Sorry about that. So as I was saying, we have, in 2 dimensions, we can have 3 reactions in the X, the Y, and then a moment about Z. And when we go to 3 dimensions, we can have forces in X, Y, and Z, and we can have moments about X, Y, and Z. So suddenly we have the possibility of 6 reactions rather than 3. We often refer to these in statics when we're looking at these problems as these reactions as unknowns. These will be things that you don't know what the forces are. You don't know the magnitude or the direction of each of these vectors until you solve for them. So if they exist, you probably don't know them unless they're given, and that's usually pretty rare. So I'll often refer to them as unknowns or reactions, sort of interchangeable. Here's an example of two different connections, a fixed connection, and what that means is it's literally fixed to the wall. It's like welded or bolted or riveted. It can't move. Rigid. If you look at it in 2 dimensions, we end up with a force going in the X and in the Y. Those would be our reactions, and then also a moment. So we would have 3 reactions for a fixed connection. And again, I'll go over this in a little bit. But this is sort of the diagram on the left, and this is what you're looking for. You're going to, in your lab here, we're going to draw these little diagrams of what the reactions are on each of our connection joints. Now, if we look at the same thing in a 3-dimensional aspect, where we have a bar coming down that's welded to a surface, you can see that, again, we basically stack every single response here. If we go back up to the top here, in the 2-dimensional thing, for the fixed, we had Fx, Fy, and Mz. This would be Fx, Fy, Fx. I'm doing it backwards. And then moments. In the 3-dimensional, we do the same thing. We have the ability to have a reaction in every dimension possible, both in linear forces and in moments. So we have 6. If you count them, we have X, Y, and Z in terms of linear forces. And in terms of moments, we have Mx, Mz, and Y. If you count those all, you get 6 unknowns or 6 reactions. So keeping track of those is kind of important. When you're drawing free body diagrams, this is what you're going to end up drawing on your free body diagrams, are these reactions. And I've said earlier, if you can't draw a good free body diagram, you're never going to solve the problem. So. All right. So on to the next page, and I'm just going to briefly go over this. This page is mostly for your reference. If you get lost in this lab and you're not following along with me, I have recorded all 13 types of connections that we are going to cover in this lab. We are covering 13 types of connections today, and all 13 of them there have a short video that you can go and reference. I've also put 2 documents there that you can also pull up and look at. The first document is connections, and it will have a whole bunch of these connections, and there may be some that we're not covering today, as well as many that we are. And it will do just sort of what I just showed you in a diagram there. It will show you what the connection looks like diagrammatically, and then also it will show you the reactions drawn with little arrows superimposed on top of the diagram. And then lastly, there's a bunch of free body diagrams using different types of connections from forces. That's not what we're going to cover today, but I want you to know that that's there. It's a good reference for the future when you're starting to draw free body diagrams that use connections. You can come back and look at that. So I would keep that in your pocket. That's a good thing to keep. So you can see I've got all of these lovely things. So now we're going to get on to the actual assignment. We've got a lot to cover today. And if you just follow along, you'll be able to finish this today by the end of the lab. So there are 2 documents there. You can either download the PDF or the Word document. And I strongly suggest that you do that now. I'm going to give you a couple of seconds to stop hearing me and download that. Make sure you've got that all downloaded, because you're going to need to write into that today to hand back in. So I'm going to stop sharing my screen and give you guys a couple minutes to download those. And when you've got that downloaded, give me a thumbs up in the window or give me a chat, yes. And then we'll proceed.
Print it out and turn it in?
No, when I say print it out, I'm speaking in a digital sense. Download it on your computer. You'll either, if you want to print it out and write physically on it, that's fine. I think you may need to do that. Some of you, I've seen a lot of you able to write. That's probably the best way to do it. Or if you can do it digitally and write on top of it, that would be great too.
Oh, sorry.
Go ahead.
The second one is just like a Word document with like a link attached to it. Is that right?
It should just be a Word document. They should be the same thing, just one's in PDF and one's a Word document.
Oh, got it. Okay.
They're the same.
So they're the same thing though. If one works for me, I don't have to worry about the other one.
Correct.
Okay.
It's just an option, depending on what suits you best.
Cool. Thank you.
Yeah, it should look like this. So in each, let me pull it up on. So it should look like this. This is the Word document. What we're going to do is you can put your name in there, and today's date. And what we're going to do is we're going to fill in these columns for each of these types right here. So there's 13 of these boxes, 13 rows. The first row, the first column is the type of connection we're looking at. The second one is whether it's going to be done in 2D or 3D. And then we've got 6 columns. And you'll note that it's FX, FY, FZ, moment about X, moment about Y, and moment about Z. If it's a 2D, you'll immediately see that I've eliminated the fact that there's any forces in the Z and there's any moments in X and Y. So that gets us down to only 3 reactions. And so what you're going to do is basically just put a check mark in there or a yes. Does the reaction for that connection exist or not? And then I want you to sum up the number of yeses or the checks that you've done there. And then lastly, what I want you to do is to just do a real quick diagram, and we'll go through this. I'm just saying how it's going to be done. There's a little diagram here right below the pin type there. In that big box there should be room to make a quick little diagram. All right. So I'm going to move on to the very first type. Change cameras here. All right. So the very first one, if you've got that sheet loaded, everybody has their sheet loaded, I hope by now. What we're going to do is we're going to look at what's called a pin or an ideal pulley. And let me draw diagrammatically what that looks like. So this is a pin. Typically, so you've got a surface, you've got a little triangle you draw, and then you've got your beam, and this would be your connection right here. Sometimes people will draw a pin with a little ball through there. I personally draw it this way. But when you see that diagram, that's what it looks like. So what does it look like in reality? This is, let's do it this way. A pin really is a hinge, but only in 2 dimensions. So we're looking at it this way. We might look at it directly on. Can you guys see that? I struggle with not being able to see my camera on there. So it's a pin. We've got a fixed portion and something that pivots. Or in the pulley, this is fixed and this can rotate. You can see this is a pulley. All right. And so what we're going to try and establish is how the forces in 2 dimensions, what forces can possibly react with this. So if I'm looking at moments and I try and create a moment, clearly I'm able to swing this piece back and forth. And so there's no moment resisting. So there's no reaction in the moment. All right. There's no moment in the reaction. No reaction that's a moment. But if I pull in X or push in X or pull in Y or push in Y, I'm getting resistance. And so I'm getting a reaction. So typically what we would do, and I'm just going to start this as sort of a standard. I'm going to draw my frame of reference. This is X and Y. And what reactions do we have? We have, so we had a reaction in the X. We had a reaction in Y. So we have 2 unknowns. Now, you should be able to just start filling in your sheet right there with just that. So my first thought is to stop and ask, are there any questions? If you're not understanding what I'm talking about, now is a good time because it's going to go kind of like this for another dozen times.
Rob?
Yeah.
So these reactions are just forces, right?
They are forces that could exist in that joint.
Okay, possible forces.
Yeah. So like when I talk about there was no moment, we try and put a moment on this and it's going to swing, it's going to move. It's not going to be, as we say, static. So that's why we say there's no moment reaction here. There's no force resisting this turn. There's no structural member resisting that. Mm-hmm. But there is in the X and in the Y.
Okay.
What we're looking for is forces that are resisting or reacting to a force. All right, the next one, we've already sort of done this in 3D. We did this on the very first page, but let me show you what it looks like. This is a fixed reaction. And for whatever reason, I've never understood this, but fixed reactions seem to confuse students. They seem to miss this one all the time. But let me first get rid of my drawings.
So Rob, just to clarify, yeah. we've completed the first section of the worksheet, right? It's just the check marks and it's 2 and a little sketch of it, right?
Absolutely. That's
okay,
it.
Cool. Thanks.
Yeah, like I said, if you just follow along and do this, the whole point of this is that people remember things better, and it's been proven in studies that if you write things down, that somehow your brain remembers them more than if you just listen. Which is the whole purpose of taking notes in class. But this is sort of a forced taking of notes today.
All good.
Of course, you would remember better if you were actually here physically able to experience them, but I'm sorry we're not able to do that today. So what is a fixed connection drawn like? Typically, that's it. This is a fixed. And again, this is in 2D. So what does it look like? It looks like this. This is just a rod that's stuck in there, and this, of course, you're seeing it in 3D. But if you're looking in 2D, it would be like this. You see it bolted in. And so, again, we're looking at the 3 possible reactions that we could have. And of those, let's look at X. That would be me pulling or pushing on this. And clearly, nothing's moving. And so I'm getting a reaction when I push on it with an X force. I get a reaction. It's pushing back. And if I push on it with Y, again, I'm getting a reaction back. And lastly, if I try and turn a moment, I'm also getting a reaction. So this is actually getting a reaction in all three of our possible outcomes here. So again, let's just draw our coordinate system, x, y. And what does our reaction actually look like? Our x, our y. And we've got to draw a moment because we said we have a moment. And which way is positive? Using your right hand, coming out, go around. This is a positive. MZ. So we have 1, 2, 3, 3 unknowns or 3 reactions. And I'm going to encourage you to always draw your reactions in a positive sense unless you have good reason to do otherwise. And there's very few good reasons to do otherwise. So you notice I did X this way, Y that way, and MZ this way. All those are considered positive in notation. All right, letting everybody kind of catch up there for a little second.
How come you didn't push it in the Z direction? Wouldn't there not be a reaction either?
The question was, if I understand correctly, why didn't I put in the Z direction?
Yes.
And the answer is right now, we're looking at this in a 2D sense. We will look at this in a 3D sense a little later on, and we will draw all 3 dimensions.
Okay.
All right. Well, I'm gonna, if everybody's got this, and again, like I said, if you can't keep up and you get stuck behind, you can always go check the videos. I've basically done this exact same thing in the videos.
Rob, I realize I have a question about the hinge.
Yes.
So you were holding, when we say Fx, that's applying a force in the X direction to the plate, the vertical plate. Yeah, there you go. The vertical plate in your left hand,
Yeah.
right? And you're fixing your right hand.
I can, let's call this one fixed here down low,
Okay.
and we'll call this right here. So we're pushing this way. And also if I pushed up, you see it's rotating, but that's a moment. If I were to try and pull straight up on it, it wouldn't move. Or if I try to literally lift straight up, it wouldn't move. And so I'm getting a reaction in the X and in the Y.
Okay. Okay. So you, okay. So the, okay. All right. And then I think that clears it up.
Yeah, so there's the moment, you know, if I try and rotate it, it rotates. There's no resistance to the rotation.
Technically, right. Sure. Ignoring friction. Okay. So that
Yeah,
would
when
be
we
that.
look at
That, but that's MZ, isn't it?
Wait. We haven't put any, if we were to have MG on that, it would just be straight down. And
Oh,
it would resist.
MZ. MZ. Sorry. Moment
Yes,
about
MZ, yes.
Right.
That's MZ. So MZ would be, there is no reaction MZ, so it's non-existent.
So it's interesting to me because we aren't considering FZ, but we do populate the MZ for a 2D drawing.
Yes, in 2D, remember we were doing 2D moments, because there really is no such thing as a 2-dimensional moment.
Yeah.
But it's just a 2D problem. So when we're looking at things in 2 dimensions, the moment literally is always coming in or out of the page. That make sense?
Yeah.
Yeah.
Rob?
Yeah.
So on that hinge, if it was being used on a door, right, there's a force in the Z direction going down, right? And that would create a resistance moment along like the axis of the hinge. But we're not focusing on that right now.
We're not looking at a 3-dimensional problem.
Okay.
If
Yeah.
you were looking at the door as a 2-dimensional problem, you would be looking at from directly above or directly below.
Right. Okay.
And we're not doing either. We will get to the 3-dimensional hinge.
Cool.
And it's kind of a shame because my lab last week was 3-dimensional moments, and the whole point of that was looking at a door hinge. So. So I think we're up to smooth collar on a smooth shaft. Let me draw that up. So we've got a collar, and we've got a fixed stick on the collar, and we've got a shaft. All right. So this is a collar on smooth shaft with what do they call it? Fixed support. All right. So this is going to be our collar. This is our little fixed support here. So if this was just a 2D problem like we're looking for, this would be the fixed, and this would be that same look that we looked at just before with the fixed. So this is the shaft, and you could basically create a reaction in every direction. But we're going to go put this on a shaft. So now this collar can slide, and we're just going to look at it in 2 dimensions. So we're going to look at it this way. So we're looking at what reactions we might have. Now, before we start looking at this, we can see that if I pushed on this like that, push straight down, and I can't pull it because it'll pop out. It's not very well attached. You can see that we can have a reaction along this way, and if I push this way, it's going to slide. And so what throws people a lot in this particular case is they want to draw X and Y this way. What you want to do here is you want to draw your orientation different than you did in the last one. Let's call this X. Call this Y. All right. So now when we go back and we look at this, when we talk about pushing an X, it slides and so it moves. So we have no reaction. There's no force resisting along the X direction. And if I'm pushing in the Y, there is resistance. And if I try and rotate this thing in about Z, it doesn't want to rotate. So what are our reactions? So again, I'm going to draw like this. We're going to call this RY. And I said that I had a moment, because it resisted the moment, about Z. But I had no force in the X. So what if the rest of your problem is oriented with X and Y this way? If you were to actually look at this problem and you were to try and draw X and Y, if you went and you broke X into components and Y into components relative to these two, you'd find that the Y component of X is solid, but there would be no X component. And then of course here, the Y component, the only portion that would exist is this, and there would be no X component. But the best way to do this, like I said, is to rotate and draw it this way. And you'll know this angle in your problem, so you'll be able to figure that out. So draw it like this, orient it along the actual axis of the shaft, and do your reactions that way. Did I lose anybody on that?
You say it resists a moment in the Z?
Yes. So we look at this.
Whoops.
Lost my shaft. It is
Kind of weird
shaft.
because obviously a 3D object in a 2D.
So when we go to
sense.
3D, it'll look
Yeah.
different. So Z in this case is coming straight out,
Uh-huh.
and we're trying to rotate either part relative to each other, and assuming that was fixed, it wouldn't rotate.
Uh-huh. But why did you not note the moment in the Y?
In a 2D problem, we don't have that.
There are no moments in Z. If we had a 3D problem, we would. That would be about this axis, right?
No,
Yes.
there are no moments in Y.
Yeah,
However.
and it would also resist, but we're not drawing that because it's a 2D problem.
Very well. So I should put not applicable for MY.
Yes, it should have, if you look at your sheet, MY should have a NA, right? MX and MY should have NA.
Yeah, indeed it does. I made my own sheet because I can't write on the PDF. But yes, it does.
So the next thing, let me erase. The next one is similar. It's a collar with a smooth shaft with a pin.
If it springs to mind, where would you see something like that?
Which? The last one?
Collar, shaft with a pin.
I've seen a lot of those kinds of things on like transmission shifting gears, where you basically are rotating something and then sliding it forward. So if you were operating a gear shift, you might see something like that. All right. So in this case, we've got a pin in the middle of our collar. And there's our shaft again. So what I've got, in essence, you can kind of see here in 3 dimensions here, is I've got a pin that allows me to rotate this way and allows me to slide this way, but I can't pull or push this way. So again, let's reorient our axis. So this is again X, and this is Y. Make life easier. So if we look at linear forces in the X, which is along the shaft, we can see that it slides and there's no force resisting, there's no reaction. So it's just sliding along there. Or I could do it upside down like this, so you might be able to see it better. There's nothing happening. Now about in the Y, if I push perpendicular or pull perpendicular to the shaft, I get a reaction. It's resisting me. It's not allowing me to do it. So I'm getting a reaction. I'm getting a force pushing back on my force. And if I try and rotate about Z, it rotates freely. So what are our moments?
I have a question. Does the pin rotate all the way around, or does it matter if the pin has like a can rotate 360 degrees?
So you're asking, does it matter if it rotates 360 degrees?
Yes.
And the answer is technically no. In most designs, you would design, if you were actually designing this, you wouldn't design it so it hits a stop. That would be, then you would start to have other forces on your component. The whole point is usually to put something like this rotating is to eliminate the moment from one part translating to the other. So you wouldn't, even if there was a stop, and we'll cover this a little bit more further on, but if there was a stop, we wouldn't include that unless we were saying it was pushed up against a stop. Typically you work in the middle of your range, and so it doesn't really matter whether it rotates 360 or not. You're just saying it rotates.
Okay, that makes sense. Thanks.
So we're going to have, we said we had a reaction in Y, We had no reaction in X because we slide along, and we had no reaction in the moment. So the only reaction we've got, and I should have been putting this all along. I didn't know if I put this in the last one or not. One unknown. Or one reaction.
And why do we call that an unknown?
An unknown. So when you're doing statics problems,
Mhm.
let's let me give you a very, very quick look into the future. You might have a beam, and it has two pin supports, right? Can you see that? Just want to make sure we're.
Yep.
And we said that there were no moments in pins that we would get a reaction this way, and this way, this way, and this way. That would be R1Y, R1X, R2Y, R2X. And let's say we applied a force like this, F1. And I said,
so
we
it's
wanted
when
to
you're
know what was happening at each of these spots. We'd have to know what the reactions were.
equal and opposite reactions like in equilibrium equations. That's what we.
Yes,
That's why we're calling these are the unknowns when doing equilibrium equations.
absolutely. That's exactly right. So what we would do, and this one, I hate to say it, is unsolvable. This would be two unknowns here, and this would be two unknowns here. And we end up with having only three equations to solve with. We have the sum of the forces in the X to equal 0, the sum of the forces in the Y to equal 0, and the sum of the moments in Z should equal 0. So if we do this equation at 0 equals 0, here we would have R1Y plus R2Y. And here we would have R1X plus R2X. So what we really have are two equations and four unknowns. That's a bit of a dilemma, as you know. Once you have more unknowns than you have equations, you can't solve it.
Plus the sum of the component of the forces too, right? Of the
Okay.
F1. Oh, can you hear me?
Those will be
I can't,
known.
I'm
We
not
would
sure I
know
understand
those,
the
right?
question yet.
Never mind.
So that contextualizes it really well for me. Thank you.
Okay, yeah, sometimes it's hard to see in context why you're doing this, but ultimately what we're trying to do is we're trying to discover how many unknown reactions we've got in order to solve the forces at all of our different different supports.
Wait,
And
I
when
have
you
a question
Whoop.
about that.
Go ahead, me.
Oh, sorry. Are those are two pins, right, that are connected by something?
Yes,
And they don't experience a moment in the Z?
no, pins do not. They are like our hinge. They would be like this right here.
Uh-huh.
So we would say, oh, there's no, they can't resist any moments rotationally.
Okay, so because those things are isolated, like I was just thinking, like if you push on one end of the bar or if you pull on one, like push up or down, then you're creating a moment on one end of the bar that's connecting them.
You
But-
are, if we looked at the components here, right? You said that we had components of F, right? Like this. And you're right, right here we have a moment, we have a force and a lever arm. And we are creating moments, but it does not translate to the support.
Oh,
That support cannot resist that moment. We have to find some other way to resist that moment. And usually the way that is that you have a force here creating a counter moment. That vertical force in that lever arm is creating a counter moment, and it'll actually be proportioned between these two, because we'll get a moment this way and a moment this way to create something that counters that moment, but it's not a moment at the connection.
Okay, I see. 'Cause
Does the moment, like in that piece, because you have the, you know, whatever the attachment is between the two pivots, like wouldn't there be
Yes.
internal forces though that you're introducing into that when you try and
So
rotate
yes,
it?
there will be internal forces, but in statics, when we draw a free body diagram, we never draw the internal forces. We will later on, at the end of the class, we'll start to look at internal moments. We'll look at shear and bending moment diagrams, and we'll look at what those moments are doing across the length of the beam. But in order to solve that, we need to be able to solve for these reactions first.
Got it.
All right, let's go on to rollers and balls. Those are all good questions, guys. I'm glad you're asking them. All right. So we've got ball, roller, and a rocker. And that's not Eddie Van Halen. All right. So how would we draw that? We would have our bed here, and we'd have a ball. We put our beam on top. Or for a roller, what we typically will do is we'll draw a hinge that rides on little cartwheels, or this is our beam. Lastly, and I hate the rocker, so those are the three sort of diagrams that you'll see. And this is a classic case of a roller. It's just a rolling wheel. So what happens at a roller? So we can push straight down. If we try and push horizontally, it rolls. We push straight down, it resists. And if we try and rotate it, it rotates freely. So we look at this again, we'll define X, Y. And so we said that we have only a reaction in the Y.
When we draw a diagram of this, does it have to be straight up?
If you drew these straight up, yes. If they've got it at an angle, no. You could, you can always define it differently. If you decided to, let's say you decided to define this this way. The problem with that is that when you slide in this direction, you'll have some component of this and some component of this that contribute to each of those. And when you try and push down, you'll have some vertical component of this and some vertical component of that. So that's why whenever you see these sliding things, like in that shaft on the, the smooth collar on the smooth shaft, try and line it up with the direction that things want to slide. So this is probably not a good idea. I would go this way. Just to kind of further the way that you'll see a lot of problems in the future, I draw my hinge. And as we said last time, we had R1Y, R1X, and here we would just have R2Y. So in this case, we only have one unknown with the rocker and ball. And so by using these two together, and we tried to solve this using the sum of the forces, we would have 1, 2, 3 unknowns. And we would have our 3 equations, which would be the sum of the forces in the X, sum of the forces in the Y, and the sum of the moments. So we would actually be able to solve this. And so you'll see a lot of problems in the near future that have these two supports.
Wait, just to clarify, so the ball and the roller, we're seeing them as one system? Or,
So all 3 of these are the same thing.
oh, okay.
All of them are diagrammatically the same. I don't particularly like the rocker. For whatever reason, they love to include it. I don't see too many rockers.
I was just gonna say, I don't know what a rocker is.
It's like a rocker, like a rocking chair. It's got a curved bottom and allows it to basically rotate.
It's like
Yeah.
a section of a wheel that would be connected to that pin you see on the lowest drawing there.
Come again?
Well, it's like a 50 or 60 degree section of a wheel. It's like you took a wheel that was connected at that pin to the
Yes,
bar and then removed everything but 60 degrees of it.
that's correct. It's like a pie slice of a wheel, like a pizza slice.
Sorry, could you re-explain why there was no reaction in the X? I guess I kind of just missed it.
Okay. We've got our roller. If we push on this, it's going to roll, right? And so we're not resisting. So it's basically sliding along the X.
Right, I figured. Does that mean there's no moment about the ball and rocker in the Z?
In the Z, right? Because it rotates as well.
Wait, so
But
there
not
is a
only, but not
moment?
only does it roll, but it rotates. So both
So
of those
the
things.
question is, does this connection resist this force? And
No.
right, that's what the question is for this whole activity is. So does it, if it resists that force, then we put a check, basically.
Yeah, that's a reaction.
Gotcha. Okay.
Yeah, sometimes that point is evasive. So the next one is a pin in a smooth guide. And let's, so if you want to look at this as that's a slot. And this is your pin. And this is just some arm. So really, if you look up at on the same page, you look at collar and smooth pin, smooth shaft with a pin. They're really the same thing. So first of all, let's look at just here might be something that slides along inside, just a slide. And if I were to use this mounting hole as a pin, I could have something that rotates on there. And really what that looks like is this all over again. So we basically can slide along the slot and we can rotate this way, but we can't push perpendicular to the slot. And in fact, if you push if you're off a little bit, they would slide along the slot. So we want to push directly on it. So it's really the same identical situation as the one above, the collar with a smooth. So we do the same thing. Make this X. Make that Y. And the only reaction we're going to get right there is going to be RY. So we have one unknown. All right, now we're moving on to 3 dimensions. So anybody need a break? Am I getting too boring? Maybe I was boring to start with. I don't know.
Doing great.
Just to
You're doing
review
great,
that,
Rob.
For that last one, how many unknowns did we have?
Like I said, it's only one, and it's identical to the one above the smooth collar on a smooth shaft with a pin. They're identical. They end up resulting in the same concept, same result.
Okay, thank you.
So we start drawing in 3 dimensions, things get a little more exciting. So we've got a rod that comes down, and it's usually necked a little bit. And then there's a ball. And it usually fits in some kind of socket. Have it be on some sort of plate. And this is ball and socket. And for those of you that have hatchbacks that lift up in the back with gas struts, usually at one end, we'll have a ball and socket attachment. Now I've got a very tiny ball and socket arrangement here. So I'm gonna hold it, hopefully not too close. This is a ball and socket arrangement. If I peel back this rubber boot, you can kind of see in there's a ball in that socket. And other balls and sockets are your shoulders. Right there, you have a ball and socket in your shoulder. So there's right there, inside of your shoulder, there's a ball and a socket arrangement that goes out to the rest of your arm. So in case you're wondering what they look like. So in a ball and socket arrangement, we look at, let's call this X, doesn't really matter. We can see that we can rotate this quite freely. We call that X. What about Y? If this is X and then this is Y, can we rotate about Y? So rotating about Y would be this way. So that would be rotating this way, back and forth. So most people get a little confused. Yeah, I am rotating here. I'm rotating only about 10 degrees, but I'm rotating. You would design, again, you would design it so it was in the middle, but if some rotational force were to come down, it could rotate a little bit. It would not translate that rotational force to the piece that I'm holding in my left hand. So we have no rotation in Y, and now we have one in Z. If we look at Z, would be coming out this way. So X, Y, Z. You can see that I can also rotate about Z. Not a lot. Now it does eventually hit the stops, and it would then no longer resist. But we're looking at the middle portion, and we're saying that no moment is translated through that range of motion there. And that's how we design these things. We design these things to be in the middle of the range of motion. So we're not translating any moments. If we pull an X or push an X, you can see that I'm getting a reaction. And if we push in, which way is Y, I said. Y is this way. If I push up in Y, push straight up, it will resist. And again, in Z, coming towards you, it resists. So let's kind of draw this. X, Y, and Z. So what reactions do we have? We said that we had reactions, linear reactions in all our X, our Y, and our Z. And then we said we had no moments in any of them. So we have 3 unknowns. Any questions on that?
So for that one, you sort of glossed over which axis was which, but on like the next one is a hinge. I think it's going to matter which way we line it up. Is that right?
Correct. It will matter in the next one for sure.
Okay, thanks.
Yeah, because the nature of this, that it doesn't have anything in any preferred direction in terms of moments and or linear forces. It doesn't really matter. Clearly, though, you want to design it so that you're in the middle of your range of motion. You wouldn't want to design it maxed out already, or that would defeat the purpose of having this kind of connection.
I'm unclear on the moments section for this one.
Yes.
Depending on how you orient your axes, it would at least resist one of them.
I'm not quite sure. So it wouldn't matter really, if I choose X this way and Y this way and Z this way, or even if I chose to put it at an angle, I'm still going to be able to rotate in all 3 dimensions. I can rotate any way I like. In fact, you can see I'm prescribing a circle. At some point, I'm creating a moment in all 3 axes by doing this.
I see. Okay, so we could kind of think of this like Joanne says, if you put a screwdriver in that up like on the ball, it would rotate. Like, if the ball itself had like a little Phillips indent where you could insert the head of a screwdriver, you'd actually be able to rotate the ball. And that's a way to think about how in any X, Y, or Z, you'd be able to rotate the ball.
Yeah, the ball should be able to freely move within the socket.
Okay,
just like in your arm.
So
you can rotate this way. You can rotate, this way. Rotate this way, and this way. But if you pull on my arm, or you try and push on my arm, or lift on my arm, or whatever, It doesn't move. So your arm is able to rotate in all three directions. Let's draw our hinge. Let me find my hinge again. So this is our hinge. And let's examine each of the three dimensions. So let's first, as somebody said, let's define our dimensions. Again, we want to, if we can, some axis along this pivot point. And so I'm just going to arbitrarily assign this to be X, Y, and Z. So if we look at this, let's talk about forces. Let's just talk about linear forces first. If I push on this, the whole thing's got to move. If I'm screwed into my door, the whole thing's got to move. I got to move the whole door. I'm getting a reaction. And again, same way here. If I'm pulling on the piece, or if I'm pushing straight down, so I'm getting a reaction in X, Y, and Z in terms of linear, all three of them. But what about moments? Well, we've already discovered that in this direction, there's no moment reacting. We have no moment in the X. But if I try and rotate this about the Y, it would be fixed to the door and it wouldn't rotate. Now, if I tried to rotate it about Z, it would rotate, it would not rotate. Again, it would resist my rotation. So what do our reactions look like? And we said that we had a moment about Y. And so again, up. And so we're going to be going that way. And Y. And come this way. And Z. So we have 5 unknowns or 5 reactions. Everybody ready to move on?
Sorry, could you just go over the moments one more time? Wouldn't the rotation be about the X? Right, if the hinge flips up.
That's the one that's free, right? So we're tracking
That's the
ones
one
that-
that's free,
that can't
correct.
move.
Oh, yeah. I'm sorry, I keep forgetting.
No. This is why we're doing this, is because people get those confused. So yes, when it is free to rotate, there is no reaction. It's when there's a resistance to the rotation that we get a reaction.
Yeah, I got it.
Newton's law, equal and opposite. So the next one, I'll say something about some of the names of some of these things coming up. There are multiple names, and some of them I don't like. I don't ever refer to them in the way they refer to them, but I will try to refer to them in both ways so that you're familiar and you don't get caught out at some point. They're calling this next one a journal bearing. And they call it a journal. And I call it a plane. So this is what the bearing looks like. And the reason that it's often called plane, particularly if you're searching through McMaster car and such, is there are no ball bearings. There's nothing fancy about this. It's just a smooth, low friction surface. In this case, it's bronze. It's probably impregnated with oil to make it nice and smooth. But it's just a plane. They call this a journal bearing. This is a plane bearing. And often, this alone is often called a bearing. This particular structure around it is often called a pillow block. So this is a journal or a plane bearing inside of a pillow block. So not to get too confusing. So if we put our shaft in there and we want to know what forces it resists, let's again start off by defining our directions. So I'm going to call this X, Y, and Z. We'll go back to our part. Now, if we push in the X, it slides right along. So we have no reaction in the X. If I push in Y, straight down, it's kind of hard to see, my finger gets in the way. Push down this way, I get a reaction. And if I push this way, I get a reaction. So I'm getting a reaction in Y and in Z. Let's look at moments. Clearly, I can easily rotate this part about X. If I try and rotate it about Y, which would be this way, if the pillow block is mounted properly, it won't rotate. And again, if I try and rotate about Z, again, it won't rotate. So what do my reactions look like? I'm going to have a reaction in the Z, a reaction in Y, and then I'm going to have a moment in Z and a moment in X. I have nothing in the X, excuse me, Y. I have nothing in the X. So I have 1, 2, 3, 4 unknowns.
It's an unknown.
Any questions? All right, the next one gets a little exciting. Well, depends what you call exciting, but I find thrust bearings exciting. I'm getting ready here, so hold on.
Hey Rob, I have a question.
Yes, please.
So I've noticed that we have always had a reaction in the Y direction. Is that normal? Is that safe to assume that there will always be a direction in the Y or force in the Y?
No.
Okay.
It might just be partly the way I'm choosing an orientation of the axes. That's just coincidence.
Okay.
So what is a thrust bearing? Let me kind of show you all the different pieces for a thrust bearing. So basically, we're going to take our plane bearing, our plane journal bearing, and we're going to install some pieces on it. We've got this little disc with a bunch of ball bearings in it, and we've got two. These aren't really washers, these are surfaces for these ball bearings to ride on. So what I'm going to do is install them on my plane bearing. I got this, and I slide my surface on. I slide my ball bearing surface and then my other riding surface. And then I'm going to put a locking collar on it. Tighten that up. And then I'm going to do the same on the other side. So again, I install surface to ride on.
And so this thrust bearing, does it like lock it in place? I'm not sure what it does in the first place.
Yes, that we're getting there. And yes, you're correct. It locks it in place.
Okay, so we're gonna have a.
Blocks the shaft from sliding along the x-axis.
Okay. Does it prevent it from spinning on the x-axis as well?
That was the whole point of those little balls inside the blue piece.
Okay.
Is now you can see that I've got this assembly. You see it fairly rotates, and you can see that it doesn't want to slide in and out any longer.
Okay. So we now we have like an R in the x-axis.
So yeah, you're on it. So yes, so if we look at this again, we look at the exact same configuration. We push in X. We have a reaction in the X. We still have a reaction in Y. We still have a reaction in Z. When we look at moments, we know we still have no moment around the X. We do have a moment around Y, and we do have a moment around Z. So thrust bearings are used if you've got some force usually on your shaft. They'll use these in transmissions and in clutches and throw-out bearings. In fact, that's what a throw-out bearing is. It's a thrust bearing that allows your drive shaft to go forward and backwards. For those of you who've installed clutches. So let's look at our reactions. So we do have an Rx because of our thrust bearing now, Ry and Rz. And we still have a moment about Z. We still have a moment about Y. So we have 1, 2, 3, 4, 5. We have 5 unknowns. So just so you know, when you're looking at problems and you see a thrust bearing, you should probably be unhappy. The reason being is that you now have 5 unknowns. And when we go back to that first page and we said we basically have 6 equations that we can deal with. When we're looking at our statics, we can use the sum of the forces in the X, some of the forces in the Y, some of the forces in the Z, and we also can get the sum of the forces, some of the moments in the X, some of the moments in the Y, some of the moments in Z. So these are our equations that were available to us. So if we see a thrust bearing, we've already used up 5 unknowns. It means that whatever connection we have beyond that had better only have 1 unknown, or we're not going to be able to solve it. So this is what happens in 3-dimensional problems is you get, in a 2-dimensional problem, you get fx, fy, and mz. When you get to a 3-dimensional problem, you gain 3 more equations. You get mx, my, and fz. So just kind of keep that in the back of your head for upcoming problems. Everybody get this one?
Yeah.
Okay.
Looks good.
I don't want to go too fast. There's a tendency to talk too much. And when I talk for more than 15 minutes, what I've discovered is people start to fall asleep. And it's not just because of me, but it's just sort of standard that when somebody talks for 15 minutes or more, the audience just drifts off, no matter how exciting, unless they're using fireworks or something.
You're doing great, Rob. Keep it up.
Rob, I have one question.
Yes.
I was thinking about someone brought up a question about like restricting moment in the y-axis, and I was thinking like, what would be a connection where you would want the y-axis to move freely, like because most parts you would want to resist gravity. You know what I mean? So like, wouldn't you always want to restrict the y-axis?
So have you guys seen 3D printers? If you've seen a 3D printer, they usually set up a carriage on top. And it usually has plain journal bearings. Oh, this is not drawing well, I didn't draw it yet. And they'll have a wall right here, and another wall. And so the carriage will slide back and forth, and then usually they'll have some sort of belt drive for the motor, so they can draw it back and forth. And then they'll do the same off of here. They'll have an attachment, and then they'll have another carriage with plain bearings. And again, some sort of either lead screw for the motor, usually a stepper motor. And so they can drive this up and down. So this connection right here is oriented in Y or X or Z, depending on how you do it. But basically you end up being able to, at each moment, slide in only one direction, depending on how you've arranged things. So in a 3-dimensional printer, they'll have one little gun right here that's ejecting plastic out of it, squirting it out. And so by sliding these bearings up and down with a motor, and then sliding these bearings back and forth, and then you'll also do the same this way. You'll have another drive, this motor and a lead screw. You can slide the carriage back and forth. So you end up with bearings that slide along in all directions eventually.
Wouldn't you still be restricting the Y movement because you're kind of controlling how fast it moves though, right?
So if you call if you call this, let's call this, change colors. If you call this is a terrible drawing, I'm really sorry. If this was X here, you're right, we're restricting in Y. But if we keep the same orientation, X and Y and Z, this is now X still, and now we're allowed to slide in Y. And on this carriage here with more bearings, we're allowing it to slide in Z, but not the other two. So we're just taking the same bearing and basically orienting it in different ways.
Yeah, I mean, Miles, like, even though it's not able to move without the motor spinning, like a door is not able to open without unlatching it, so it's.
Some force gets applied through the motor. And when this force gets applied through the motor, because there's no reaction in the X, it's going to move. What you don't want happening is when this motor applies something, you don't want these pieces moving. So sometimes you don't want things moving. All depends on what you're trying to do.
Okay.
While you guys are just sitting there, can you guys pull up the very the opening page to the canvas page. And on the front there, there's a picture of a guy standing next to a bridge.
Yes.
You remember that? If you look at that bridge support, you'll see that that's a pinned or bracket support. Just take a small detour here. So that picture right there, that's a giant pin. You can see the size of the guy, and he's standing at the support of a bridge. Anyways, I love that photo just because it gives you the size of which things can be in engineering.
That is impressive.
What bridge is this?
I don't know. I think it's in New York. I want to say it's the Brooklyn Bridge, but I'm not sure. I love the fact, look at all those rivets holding that thing together. Holy cow. Anyway,
It's the Bradfield Bridge, wherever
Is it?
that is. Yeah.
okay.
Reverse image search?
No,
How did you know that it was the
Oh.
Bradfield Bridge?
if you just hit view image, it'll show the name of it.
Nice.
Okay.
That's all. I'm not that good.
It must have been Joanne who put that in there because I do not know the name of it. All right. All right, the next one. They're calling it a ball bearing, and you'll see it referred to throughout the textbook as a ball bearing only, and it kind of drives me nuts. I like to call it a spherical bearing. And I'll explain in a second why. You need to be aware, a lot of times when they say this is what they mean. You should double check, especially if you get it on an exam or something. Ask them, well, exactly what do you mean by that? And let me explain. And I've got tiny little ones here, so bear with me. So can you guys see that? This is
Yeah, that's
again,
good.
this is a pillow block bearing. And in the middle there, let me come from the backside. And I don't have a shaft that fits in there, unfortunately. So this would normally be a shaft that would fit in. And the reason it's called a spherical bearing or a ball bearing is you can see that this allows it to rotate a little bit. And you can see that there's a bit of a ball. That white piece is shaped like a ball that's been cut off at the ends and then put a big hole through the middle. This is what they're calling a ball bearing and what I call a spherical bearing. And the reason I call it spherical bearing is it has a sphere in the middle of that plain bearing. This is what I often think of as a ball bearing. This is a bearing, unlike a plain bearing or a journal bearing. It has balls around the outside that allows things to rotate. This is what I think of as a ball bearing. It does not, I repeat, allow you to twist this motion. So basically, it's like a plain bearing in its reactions in the sense that it doesn't allow any moments to happen in any other direction than along the axis itself. But yet it has balls in it. And when you buy parts offline, online, they'll call this a ball bearing. And you are not getting a spherical bearing. You are getting this, not this. The reason that these exist primarily is that so when you align shafts, you can have some angular misalignment without causing the whole system to bind up. All right, let's draw this and look at the reactions. Here we are again, my fantastic drawing of a, and it's kind of got these.
What did you call the outside of the thing that it's in again? that square
a
thing?
pillow block.
The pillow block.
I don't know why it's called that. So yeah, the black part's called a pillow block. And it's just the way that they hold it. You've got the mounting holes here. This is the pillow block part. There are other ways to mount bearings. Like I said, this by itself is a bearing. Generally, you would press fit it into some part and it would just live there. And in fact, well, can't remember where the other piece went. In fact, on this plain journal bearing, well, all they've done is take a pillow block and press fit one of these guys in there. So bear with my tiny little pillow block spherical bearing. So here we go. I'm going to try and hold it close. So if we look at this, and let's try to define our directions first. If you want, rather than doing X this way, we can do X some other way so that Y comes out differently, but it doesn't really matter. A lot of people like X this way. So let's just do it a little differently this time. Actually, let's be consistent so that
Yeah,
all of the,
please don't do that.
yeah. Let's be consistent so that when you look at the table, it looks consistent. X, Y, and Z. So in X, let's look at forces in X. I can slide this in and out quite easily. Assume this shaft fits nicely. It doesn't. It's a hex key, but it doesn't. If I tried to lift in Y, it would resist. And if I tried to pull or push in Z, it would resist. So I have linear reactions in Y and in Z. And if I look at moments now, clearly the whole idea behind this is that so this shaft can rotate. That's the whole point of a bearing like this, is so things can rotate. The other advantage is now is that I'm free to rotate about the Y-axis, and I'm free to rotate about the Z-axis. So my reactions will look like, oops. I'll have an RZ, RY, and that's it. There are no moments. The moments are, like I said, is it's free to rotate. That's the whole advantage of that spherical portion in the middle, is it eliminates moments being translated. When you design with a rigid or non-spherical or plain journal bearing, any moment that's in this shaft is going to be translated into your substructure that the pillow block is mounted to. And so there's a huge advantage to having a spherical bearing in use. So we only have two unknowns.
Hey, Rob.
Yeah.
Just because someone else mentioned it earlier, so it allows moments to freely move, but obviously up to a point. But as long as the, like, we just assume that the restriction point is, you know, we say it moves freely within a certain range, kind of thing.
Correct.
Yeah.
And you will try and design your part so that you're in the middle of your range to start with.
Mm-hmm.
You wouldn't purposely design it off at an angle like that to start with.
Right.
Particularly if you were trying to put your next pillow block down here.
Mm-hmm.
The advantage of that is if I have a table and I'm putting two pillow blocks in a row to support my shaft, they can be slightly off in this rotation. Really, they can be off in any rotation and still work.
Right.
That's the huge advantage of a spherical bearing.
So if we had a ball bearing like the one that you showed us, the first example, the skateboard one, would we treat that as the thrust bearing from the last example?
You would treat this as a plain bearing or a journal bearing.
Okay, a journal bearing. Got it.
Yeah, unless there were, you know, some sort of thrust plates mounted, like on the other one I've mounted the thrust plates on.
Mm-hmm.
So these, I mounted these thrust plates on there. Thrust
Okay.
bearings.
Thank you.
All right, just for a filler while I get the next thing ready. Can anybody name the 3 ships that Columbus sailed to bring his diseases to America? You're laughing, Tim. That's a good thing.
Pinta,
Santa Maria.
Maria,
Yeah. Santa Maria.
Santa Maria.
Pino or Pinto
Actually,
or Santa
maybe.
Maria.
Can we Google? Can I phone a friend?
No, I think Gerardo, what'd you say?
Shout out.
I think you
I
had it.
think Nina's one of them.
Oh, Nina.
Pinta, La Nina,
La Niña, la
Santa
Pinta y la
Maria.
Santa Maria.
Uh-huh.
Yeah, pretty much. Yeah.
Yeah. You know, the Pinta and the Santa Maria. I don't know why I know that stuff.
Wasn't like America named after like some Italian guy named Armanio Vespucci or something? Or
I don't know. I do know that they were Spanish ships because Columbus, even though Christopher Columbus was Italian,
yeah.
he couldn't get the Italians to fund his adventure. So he went to the Spanish who were like, sure.
He didn't even go to the right place. They were trying to go to India.
Well, isn't that why they call Native Americans Indians? Wasn't that where that came from?
I think that's part of it. Yeah.
Yeah.
That's the reason
He
why.
thought he was in India and he wasn't.
Yep. He thought
And
it was
for extra credit, while we're on the topic, what type of ships were they?
Oh, I want to say galleons, but I have no idea.
Well, they're made out of wood. That's
Caravel?
Yes.
How about, can anyone name the native people who used to
Kerrville.
live in Santa Cruz?
Excellent.
Ohlone.
Good.
Ohlone had a good life until we showed up. If I had to be any person 300 years ago, it would have been Ohlone.
didn't they do trading with the Russians first? Or that
Yes.
was some, yeah, I remember going to like one of their local museums and they said a lot of these little baskets that they weaved are now in Russia.
That's interesting. All right, let me see if I can draw this. This is a smooth pin and bracket. And it's a terrible drawing. Bear with me. The drawing in your sheet is far better. So the reason they keep using this word smooth is to mean frictionless, is what they're trying to say. And I unfortunately don't have one, which is very unusual because I have tons of these at work, but I don't have any of them in the lab, which is kind of unfortunate. So I'm going to have to kind of make do. And I'm going to call this is my large pin. I took my 2 locking collars and I've fashioned it. So we'll just call this, these 2 shots for the bracket part. And then this is the arm that you see here. And then let this collar be this. So again, it allows it to rotate. And this is exactly what's in that picture of that bridge. So you can see that we're allowed to rotate this way, but we can't rotate really any other direction. We can't rotate this way. We can't rotate this way. I can't push in any of the directions. So let's draw.
Would we say the pin can move in X? Can the pin slide in and out?
The reason that it's called a bracket is that it gets bracketed so that it can't move.
Okay, thanks.
again, this is X, Y, Z. So again, if we go back, we said we can't move an X. I got a little slop because I did a bad job, but it's not intended to move an X. We can't move in Y. We try and pull it, it won't move in Y. And again in Z, if we push in Z, it won't move it either. When we do moments, we can clearly have a moment about X or X, depending how you want to look at it. We cannot rotate about Y, and we can't rotate about Z. So the reactions that we've got, and then we get a moment about Z, and a moment about Y, and that's it. So we have 5 unknowns. All right, everybody ready to move on? Any questions on this one? We're on to our last one. The sock's getting pretty dirty.
You know, they make erasers for whiteboards, Rob.
They probably do. That's good.
Yeah, but can you like wear your eraser when you're done? I think not.
Oh boy.
My son wouldn't have any problem wearing this baby.
It's like tie-dye.
Yeah.
All right, we're on to the last one. And we've already done this one. So this is your fixed support. And we just have some stick and it's fixed to our plate or our whatever we're mounted to. So this is welded, bolted, glued, screwed, unable to move. We're back to this. So we're looking at this in 3 dimensions. So this is, let's define our directions. So if we're looking at this, it doesn't really matter if we push in the X or the Y or the Z, it resists in all directions. So we had reactions in that direction, and it's the same for the moments. If I try and twist this, it doesn't want to twist in that direction. It doesn't want to twist in this direction, doesn't want to twist in that direction, and it doesn't want to twist in that direction. So we have reactions in every possible conceivable way. I really kind of want you guys to get that. I don't know why this particular support in exams throws people. I'm not sure what happens, but I've seen it over and over again that they don't understand that they have all 6 reactions. get all of them. Is that right? Nope. So we have 6 unknowns. And if we were looking at our equations, like I said before, we only have 6 equations. We have, the sum of the forces in X, Y, and Z. And then we have the sum of the moments in X, sum of the moments in Y, and the sum of the moments in Z. So these are going to be our 6 equations right here. So if you have a fixed support, if there's any other supports involved, you're not going to be able to solve the problem. Often you'll see, you should be able to solve this. If I applied a force at the end, you should be able to solve for that. You should be able to solve all 6 of these with these 6 equations and that one force. But if you added another support in there, let's say I wanted to add a hinge or a pin right there or a ball joint or anything, it would become impossible to solve. When you have more unknowns than you have equations, it's what's known as indeterminate. Hopefully at the end of the semester, we'll do a really quick lab on how to recognize indeterminate problems from determinate problems, stable from unstable. And the reason I think that's a really useful lab is that almost always people come to me and they say, can you tell me what the forces are in whatever thing it is? And it's almost always indeterminate. Almost always. I almost always have more unknowns than I have equations at my disposal. And so I end up having to make some sort of assumptions about the reactions. Which ones can I safely ignore? And that becomes a real skill in learning how to do that. So we have any questions?
I do. Since this one has all 6 reactions, would you consider like a fixed support like the least stable, or because it doesn't really allow like the translation of the forces, kind of they're all translated to that point, so it can't soak up any of like the rotation or force.
So a fixed support reaction, all 6, and so it's probably the most stable. It also translates every single force that's acted on it into the supporting member. So in some senses it's great, but in other senses it's really bad. It translates almost every single stress there is into the surrounding thing that it's mounted to. So you can find a lot of times, and somebody was talking about this earlier, I think it was Tim, I think it was you who was talking about this, that you'll end up having internal forces that exist in your members because you've used a fixed connection. I know that when I'm a big bicycle guy, when they build bicycles, particularly when they used to build steel bicycles, and when they welded them together, depending on how it was welded when it was set up, the welds tend to shrink and expand as they get welded. And so when you first heat the metal, it expands, and then you weld, and then as it starts to cool, it starts to contract, and it starts to sort of pull the whole thing around, and it's a fixed connection, and you end up with a structure that has internal stresses even though it's not loaded. And that's usually not a good thing. That means that you have pre-existing stresses inside of your structure. There are a few examples where that's good. They do that in concrete structures. That's what rebar does. They call them pre-stress. They stretch some of the rebars ahead of time so that when they're actually put in place and they're put into compression, they're still creating some stress tension when they want them to, or just the opposite. It's rare.
Hey Rob, when you build a bridge, right? Isn't one side of the bridge usually like a roller or a rocker, so that way it allows a little bit of movement when different loads are applied? so that way it won't break.
Yes, and in fact, when you go across a lot of the bridges, you'll see what they call expansion joints. And those are connections that allow sliding behavior, but they still translate the vertical forces. So the horizontal forces are gone, but the vertical forces exist in all of those expansion joints. And that's for exactly what Andrew was talking about. There are winds, there's heat, there's loads that go across it very constantly. So you want some movement sometimes. That's what you want. It's advantageous.
But if you build like a shelf that's not going to have that much load on it, then a fixed support probably isn't the worst thing.
No.
Yeah.
I've definitely built some structures in my life that are pre-stressed, but not on purpose. So that's it for today, guys. Just hand those things in. I assume, like I said, if you got lost and you didn't fill those in, or you didn't see what I was doing, the videos of the previous page in the module should get you there. I've given everybody till about noon to do this. I hope that it's not too difficult to achieve that time, since we should be basically done now. It's just a matter of getting it into a format that you can submit online.
Rob, I rewrote the pages on my engineering paper.
That is great, Maria. Thank you very much. That'll work just fine.
Okay, great. Cool.
That actually makes me happy because that required more thought on your part. Like I said, it's amazing how when the fingers write things that the brain remembers. It's like I said, it's a known and studied psychological behavior phenomenon. That just listening is not enough. That listening and writing does a lot. And oddly enough, listening and writing on the computer, they've shown, is not as effective as writing. I'm not sure why that is, but
When you say writing on the computer, I'm assuming you mean typing.
yeah, like typing. Yeah, I guess they've shown that you are distracted with the typing for whatever reason. Your brain is otherwise engaged. I'm not sure why. Maybe
A lot of us
the
handwrite
generation
on tablets. A lot of us
Yeah.
handwrite on tablets now, which is for like as far as I'm concerned, is the exact same benefit as handwriting on paper.
Yeah, probably. Yeah, my research quotes are probably about 5 to 10 years old, and that kind of stuff didn't readily exist. Anyways, I want everybody to have a great Columbus Day weekend. Celebrate it in any way you see fit. If stomping on his statue is what you want, that's cool.
Oh, Columbus Day weekend.
Yes, Monday is a holiday. Enjoy it.
That's where the reference came in.
That's why we're
makes
talking
more
about
sense.
that.
And
No, that's
also,
good.
You gotta switch it, Rob. You gotta switch you can't call it Columbus Day anymore.
Indigenous Peoples Day, and how much more apropos is that?
Columbus Day.
Okay,
holiday.
thanks, Rob. Thanks, Rob. Have a good one.
You guys have a great day.
Thank you, Rob.
Rob.
Yeah.
So, last lab, I think I handed in late, but I was there the whole time. But I forgot to check the due date, so I emailed you and said that following night. Is that okay?
And this was the
bicycle one.
Bicycle one. Okay, Jason, that's probably okay. I haven't graded them yet, so you're kind of off.
Okay.
Right? But
Awesome.
So
just letting you know.
yeah, if you could email me one more time in Canvas, that would be helpful.
Mhm. Awesome. Thank you.
All right.
Yeah, same thing with me. I ended up accidentally missing the due date by like 30 minutes. So I sent you an email, but so you said send you an email on Canvas as well to remind you?
Yes.
Okay.
Yes.
Thank you. All right.
Hey,
Have a
Danny?
good one, Rob.
Oh, well, he's done. What's that?
Have a good one, Rob.
Yeah, you too.
Yeah, take care, Rob.
All right, I'm checking out here, guys.
You're up.
Take care.